The topic of today's video will be generating function and Rodrigues formula for Legendre's polynomials. As we discussed in our last video that Legendre's polynomials were indeed the solution of Legendre's equation, and in this video we will see that there are another ways to achieve those Legendre's polynomial. The first one is this generating function, right? So we can say that summation p and x and h to the power n is equal to 1 minus 2xh plus h square to the power minus half, right? I have replaced the suffix k by n. In the last video we used suffix k, a kth degree polynomial, but here I am using n in place of k, right? So it means that if you go and expanding this series starting from n equal to 0 to infinity, then this will be an infinite series, and this is also an infinite series if you expand it by binomial expansion, right? So these two series are same, right? Or we can say that if we equate the coefficient of h to the power n, the coefficient of h to the power n is this much, p and x, right? And when that is equated to the coefficient of h to the power n in this expansion, then we get the expression for p and x, right? So in all we can say that the coefficient of h to the power n, coefficient of h to the power n in this expansion in the right hand side, 1 minus 2xh plus h square to the power minus half is equal to p and x, right? And this can be understood in this way also, right? If we equate the coefficient of h to the power n, we will get the Legendre polynomial p and x, right? Note that I have replaced my k by n, right? Okay. So now what I will do, I will try to find the coefficient of h to the power n in this expansion, and this is a kind of +2 problem where we find the nth term or a term containing x to the power n in the binomial expansion of some function, right? So before actually expanding this function, since you can see that the power is a fraction 1 by 2, I will first write the formula. What formula will be used when we have this fractional power, right? So you have to remember this formula. Remember 1 minus t whole to the power minus half. Since here we have minus half, so I am writing the formula for minus half, and I am taking negative sign inside, right? So since the sign is negative inside the bracket and the exponent is also negative, so all terms are positive. 1 plus 1 by 2t, this is multiplied with this, then 1 by 2 plus 1 over 2 factorial t square, right? And third term will, next term will be 1 by 2 plus 1 by 2 plus 2 over 3 factorial t cube, and so on, right? So this is the expansion I will be going to use to expand this, right? So you should remember this formula, and now I will just plug the value of t. Here in my case t is actually this much. If I take h common, right, here writing my function in this way, taking h common, and I will be left with 2x minus h. So you can see that your t is this much, h multiplied by 2x minus h is your t, right? So applying this formula, and the power is minus half, yes, is equal to 1 plus half into t, this is a t, right? So that will become h 2x minus h plus 1 by 2 plus 1, that is 3 by 2, I will write that 3 by 2 over 2 factorial t square, and t square is, should be actually h square multiplied with 2x minus h whole square, right? And then you will write the nth term, right? Nth term will be, if you want to write the nth term, first you have to generalize these terms. If you see this term is the third term. Here we have h square and 2x minus h whole square. I will write that h to the power n and 2x minus h to the power n, right? So in that case we have n factorial in the denominator, right? Since we have 2, here we have 2 factorial, right? and this numerator starts from 1 by 2, 3 by 2, but what is the last term? If you see it closely, here we have 2 and this is 3 by 2, or you can write it as 1 by 2 plus 1, right? This 3 by 2 can be written in this way, or you can write it as 2 minus 1, right? So in general we can say that the last fraction will be 1 by 2 plus n minus 1, right? Generalizing this way. Okay, and if I take LCM of this thing, then I will get 2n minus 2 plus 1, that will be ultimately 2n minus 1. So I'm writing that final expression 2n minus 1 by 2, right? So be careful at this point. Okay, so this will be the last fraction, right? And this is a way to generalize it. Just write the last fraction in this way, half plus n minus 1, right? Okay, so this is the nth term, and this series goes on, right? And I will write one more term, the term before it, the second last term, and that should be the second last term would be 1 by 2, 3 by 2, and similar to that, if it is 2n minus 1, since you can see that all numerators are odd numbers, 1, 3, 5, 7, 2n minus 1. So before 2n minus 1, you should have 2n minus 3, right? 2n minus 3 by 2 and divided by n minus 1 factorial, since it is the preceding term, and here we should have h to the power n minus 1 and 2x minus h to the power n minus 1, right? So I have expanded this function, and the important point is that I have written the nth term and n minus 1th term, and be careful while writing these coefficients, right? They will play an important role to prove this, right? Okay, now what do I need? I need the coefficient of h to the power n, and this I need the coefficient of h to the power n, right? And h to the power n will be obtained from this term, and some previous term, right? So many terms will be giving this coefficient h to the power n, right? So I will write them one by one. Okay, so coefficient of h to the power n in this term, you see this term, I'm putting a tick on it, this term, right? I will write that term 1 by 2, 3 by 2 up to 2n minus 1 by 2 over n factorial h to the power n 2x minus h to the power n, right? I'm going to find the coefficient of h to the power n in this term, right? And will be given by, I have to expand this. Actually, this term is containing, this is the coefficient, but again you have to expand it by using binomial expansion. So finding the coefficient of h to the power n is not easy as it looks. So you have to expand it first, right? Okay. Is equal to coefficient of h to the power n in, I have to write the whole term, 1 by 2, 3 by 2 up to 2n minus 1 by 2 divided by n factorial, and here I have to apply the binomial expansion of 2x minus h whole to the power n. I will write just few terms, since you know that x minus y whole to the power n has binomial expansion nc0 x to the power n y to the power n minus 0, and nc1 x to the power n minus 1 y to the power 1, and so on, right? So I will write first few terms for this, right? The expansion in this way, since the power is n, the first term will be nc0, right? See the first term inside the bracket, that is 2x to the power this minus this n minus 0, that will be n, right? See the second term, that is h, and h raised to the power this index, that is 0, right? The second term will contain negative sign, since the exponent is positive and the sign inside the bracket is negative. So second term will be nc1 2x to the power this minus this n minus 1, and h to the power this lower index, right? And then so on, dash dash dash. I am not writing all terms right? I just need to pick up the coefficient of h to the power n, right? And I'm able to see that if I multiply these two terms, h to the power n multiplied by this, I'm getting h to the power n. That's why I have skipped writing all the successive terms, right? Actually, this term is also not needed. If you multiply this by this, you will get h to the power n plus 1. That is not needed, right? So what I will do, I will find the coefficient of h to the power n by multiplication of these two terms, just, right? And this is already there, the coefficient. So that is equal to the whole coefficient 1 by 2, 3 by 2, up to 2n minus 1 by 2, and divided by n factorial. And if you multiply these two terms, you will get nc0. nc0 is 1, right? 2 to the power n, x to the power n. So 2 to the power n, x to the power n, right? So this will be your first, the coefficient of h to the power n, right? Okay. Fine. Okay, now I can write this as, simplify it as 1, 3 up to 2n minus 1, and you can see that how many 2's are there? 1, 2 up to n, 2 to the power n, right? So that will be 2 to the power n factorial, and 2 to the power n, x to the power n. So this 2 to the power n will be cancelled out, right? And yeah, we are left with this thing, 1, 3 up to 2n minus 1 over n factorial x to the power n. This is the coefficient of h to the power n in one of the term, right? So I will be repeating this process for this term, right? And similarly for all the terms, and then I will add those coefficients one by one, right? So coefficient of h to the power n in this n minus 1th term, I will write that in 1 by 2, 3 by 2 up to 2n minus 3 by 2 divided by n minus 1 factorial, and we have this much, h to the power n minus 1, 2x minus h to the power n minus 1, right? So that is equal to coefficient of h to the power n in, I have to expand it, right? You can see that this time the exponent is n minus 1, right? So I will be applying this process again in 1 by 2, 3 by 2 up to 2n minus 3 by 2 divided by n minus 1 factorial, and now h to the power n minus 1, and you can see that 2x minus 1 whole to the power n minus 1, the exponent is n minus 1, so we will start with n minus 1 c0, this c, and 2x to the power this minus this, that will be n minus 1, h to the power this lower suffix, that is 0, right? Second term is negative, minus n minus 1 c1, 2x to the power this minus this, that will be n minus 2, h to the power this lower suffix 1, and then plus, and so on, right? I don't need the further terms, because I already know that if I multiply these two terms, right, then I am getting h to the power n, right? So that is my term. I am not writing the other terms, right? Okay, now we let the coefficient is equal to 1 by 2, 3 by 2 up to 2n minus 3 by 2 divided by how much? n minus 1 factorial. And when I multiply these two terms, I am getting negative sign, first of all, negative sign, n minus 1 c1, right? N minus 1 c1 will be n minus 1. N c1 is always n, right? So n minus 1, right? And this is 2 to the power n minus 2, x to the power n minus 2, right? Okay, fine. Now, yeah, 1, 3 up to 2n minus 3, and you can see that how many 2's are there? Just one less than this. Here we had 2 to the power n, 2 n times. Here we have 2 n minus 1 times, because this is the previous term, right? And this is n minus 1 factorial, and this is negative will appear here, negative sign will appear here, and this is n minus 1, right? 2 to the power n minus 2, x to the power n minus 2, right? I think this will be cancelled and we'll be left with minus 1, 3, 2n minus 3. And what I will do, I will just modify it in order to make the coefficient same. I can see that the numerator should be 1, 2, 2n minus 1. So I will try to balance this. I will multiply and divide by 2n minus 1, right? So that I can pick up the coefficient common, right? So what I will do, I will multiply this with 2n minus 1 and divide with 2n minus 1 in order to achieve this thing, right? Okay, so I have put that 2n minus 1. I will write it in bold, 2n minus 1, right? So I have to balance it here, 2n minus 1, right? And this 2n minus 1, this is 2n minus 2. I think 1, 2 will be left here, so I will write that 2 here, right? On cancellation of these two, I will be left with 1 by 2. I have written that here, and here I have n minus 1 factorial. But what I will do, I will multiply it with dark n, right? So that it will become n factorial. I want to achieve this coefficient in each and every term. So writing this n here will force me to write one n here also, right, in order to balance it. And now the remaining terms, n minus 1 was also there, and x to the power n minus 2 was also there, right? So somehow I achieved this, the coefficient which is same as the previous term, this n factorial. Now you can see that these both are same, right? And yes, this is n minus 1 2 times 2n minus 1 x to the power n minus 2, right? So what we have done so far, we have found the coefficient of h to the power n in this term, and we can continue this process in all of these terms, right? And then what we'll do, in all we will add those coefficients, first coefficient, second coefficient, next coefficient. We'll add all coefficient to get the collective coefficient of h to the power n in this expansion, right? This expansion has so many terms, right? And from those terms we are able to get the coefficient of h to the power n. So in order to get the total coefficient of h to the power n, we have to add these coefficients now, right? So I will write that process. So adding these, or I should not write adding, collecting these coefficients to get the coefficient of h to the power n in the original expansion, and that was 1 minus 2xh plus h squared to the power minus half, which is equal to this much. Now the first coefficient 1, 3 up to 2n minus 1 divided by n factorial x to the power n. Then the second coefficient 1, 3, 2n minus 1 n factorial, and then n minus 1 over 2 2n minus 1 x to the power n minus 2, and so on. There will be so many coefficients. I have only found 2 of them, right? And then I will take common 1, 3 up to 2n minus 1 can be taken common, divided by n factorial, right? And inside bracket I will be having x to the power n minus n minus 1 divided by 2n minus 1 x to the power n minus 2, and so on, right? And now you can see this coefficient. We can again manipulate it, right? You can see that there are only odd numbers, 1, 3, 2, 4, 6 up to 2n. Those numbers are missing, so I have to balance it with, I will multiply with 2, 4, 6 and so on, and divide it also. So that will become 1, 2, 3, 4, 2n minus 1 and 2n. You can see that I have inserted even numbers, right, in order to make this product complete, right? So I have to do it in the numerator also, denominator also. That will be 2, 4 up to 2n. You can see that I have multiplied with 2, 4, 6 up to 2n and divided by the same thing, right? And here I already had n factorial, right? Now what I will do, I will not write that, I will write it here only. What I will do, this will become n factorial. If you 2n factorial, if you watch it closely, 2n to n minus 1 up to 1, that will become 2n factorial, right? And in the denominator you can take 2 common, not only 2, 2 to the power n will be taken common, because they are product terms, they are not addition terms, right? If you have terms like this, 2 plus 4 plus 6, then you take 2 common and you will be left with 1 plus 2 plus 3. But if you have these terms 2 dot 4 dot 6, then you take 2 to the power 3 common, because from each term there will be a 2, right? 2 common, 2 common, 2 common, 3 2's will be there, so ultimately 1 2 3. So see the difference in these two, right? And here we have this case, multiplication case, this case, right? So ultimately 2 to the power n will be taken common, right? So be careful at this point. So when 2 to the power n will be taken common like this, so I will be left with 1 2 up to n, right? And this will become n factorial, right? Ultimately here we will have n factorial multiplied by n factorial, that will become n factorial whole square. So I will write the final term, and in the numerator I will be having 2n factorial, right? So 2n factorial and divided by, what was that? That was 2 to the power n was common, and n factorial whole square, right? I have written here only due to the lack of space. We have to do the full calculation. n minus 1 2 times 2n minus 1 x to the power n minus 2, and so on, right? And now you can see that, what is this? Pnx. This Pnx, and this is what we are going to prove, that coefficient of h to the power n is equal to Pnx. This is the proof, right? So we can say that there is a function, this function is actually able to generate the terms of Pnx. It means that this can generate P naught x. What is P naught x? P naught x is equal to 1, and if you compare the coefficient of h to the power 0 on both sides, you can see that, where is that expansion? This is the expansion, right? You can see from here, if you equate the coefficient of h to the power 0 or the constant terms, then you will get P naught x. You can see that, I will write that here only. See that, coefficient of h to the power 0, right? Okay, find the coefficient of h to the power 0. There is a constant term, right? 1, and yeah, all of the terms will be containing some powers of x, right? So only one term is there. It means that P0x is equal to 1, right? If you equate the coefficient of, find the coefficient of h to the power 1, right? Now you can see that h to the power 1 will be only obtained by multiplying these two terms, right? It means that is again 2x by 2, that is 2x by 2 is equal to x, and that is indeed P1x, right? If you equate the coefficient of h square, right, h square will be obtained from this term, multiplying these two, right? And from here also, right? I will write that. The first term will be minus half h square, right? And that will give minus half, right? And then from here you will get the first term will be, if you open the square of this term, that will be 4x square, the first term, 4x square multiplied by this much. So I will write that 1 3 2 2 2 8, and here from here we are having 4x square, if I'm not wrong, right? If you solve this, you will get 4 2 8, 3 by 2, 3 by 2 x square minus 1 by 2, this is a P2x, right? So this is what a generating function means. A generating function, in that sense, if you find the coefficient of h to the power 0, you will get P naught x. If you find the coefficient of h to the power n, you are getting P1x. Then h to the power 2, you are getting P2x. Means finding the coefficient of h to the power n is similar to finding the Legendre's polynomials, right? That's why we call it generating function. It can generate all the terms. It can generate all the polynomials, right, of Legendre's polynomials. Okay, now I will go to the second topic, Rodrigues formula, right? Rodrigues formula, right? So the Rodrigues formula is Pnx is equal to 1 upon 2 to the power n factorial, and dn dxn of x square minus 1 to the power n, right, where d by dx is the derivative. So it states that the Legendre polynomial can be obtained from this formula, right? Nth derivative of this x square minus 1 to the power n, and then multiply with this coefficient, it gives Pnx, right? So its proof goes like this. To start with this term, right? V, let we call it V. Small v is equal to x square minus 1 to the power n, right? So this is a V. What I will do, I will differentiate it, this V, 1 times, 2 times, and try to write the nth derivative, or maybe try to obtain the differential equation, right? You had done this thing in first semester course where you use that Leibniz theorem to find the nth derivative of function, right? So I am going to use that. But before that, I will differentiate it once with respect to x, right? Differentiate with respect to x. So on differentiating it, I will get the first derivative v1. I am denoting it by v1 suffix. This is denoted for first derivative, right? So v1 is equal to n times x square minus 1 to the power n minus 1, and again the differentiation is 2x, right? So we can write it as this way: v1 over n, I think 2nx x square minus 1 to the power n divided by x square minus 1, right? So we multiply this x square minus 1 here, you will get v1 times x square minus 1 2nx, and you see that this is again your v, right? Okay, right? So now I can apply that Leibniz theorem here, right, to get the nth derivative. Okay, on Leibniz theorem is usually applied when one of the function is okay, that is v1, v2, anything, but the other function is a polynomial, right? This is a polynomial, quadratic polynomial, and its second derivative will be constant and third derivative will be 0. So that's why we have a hope to apply that Leibniz theorem successively, right? That formula works well if one of the term is a polynomial, right? You can see that this is a polynomial of 2 degree and this is a polynomial of 1 degree. So applying that Leibniz rule will be good, because that will give a finite number of terms. Having sin x or cos x in one of the functions, in that case Leibniz rule is not going to work good, right? First I will write that rule. What was that rule? That rule was actually to find the nth derivative of two functions, product functions u and v. Suppose you have u and v, two functions, and they are in product u dot v, and you have to differentiate them n times. So that formula was given by Leibniz. I will write that formula first. At this point, I am leaving that. First I will write the Leibniz rule, right? The nth derivative of two functions appearing in product, right? So the formula goes, this indicates D means differentiation, differential operator, and means nth derivative, right? So first you have to be careful while choosing u and v. The second function is chosen that function which is a polynomial. So obviously my v will be this. In this right hand side, v will be x, right? So v should be a polynomial in order to apply this Leibniz rule successfully, right? So the formula goes like this: nc0. It is very similar to that binomial expansion. The first one is nc0, and you put a gap here. Then nc1, right? You give a gap, nc2, and so on, right? So when you write nc0, you have d to the power this minus this, n minus 0, that is n, and you write the first term d and u like this, and then d, this lower suffix 0, and then v, right? It is very similar to that writing that binomial expansion. nc1, for nc1 you write d and this minus this, n minus 1 u, right? And second term will be d, this lower suffix 1 v, right? I will write one more term, nc2 d n minus 2 u and d2 v, and so on, right? So this is called Leibniz theorem or Leibniz rule of differentiation, right? Leibniz rule of finding the derivative, nth derivative. But you can see that this is an infinite series in the right hand side, and it should stop, but it will stop if and only if this v is a polynomial, right? Suppose you have polynomial of degree 10, right? Then you will be going to obtain 11 terms, right? Because d to the power 10 of v will be a constant, but d to the power 11 of v will be 0, right? So be careful while choosing u and v. Here in my case, my v will be this x square minus 1, right? Okay, so I am going to differentiate this using Leibniz rule, right? Differentiate n plus 1 times this equation, right? Using Leibniz rule, right? So I have to differentiate n plus 1 times, right? Okay, so that is d n plus 1, this n plus 1 derivative of this thing. So this is my u and this is my v, right, is equal to, since 2n is a constant, we will write that outside the derivative, right? And d n plus 1, the first function and then second function, right? Now n plus 1 c0, you can see this formula, n plus 1 c0, d this minus this, that will be n plus 1 of v1, and d 0 of x square minus 1, right? Okay, plus n plus 1 c1, right? And d this minus this, that will give you n v1, and d 1 of x square minus 1, right? Third term, n plus 1 c2, d this minus this, that will give you n minus 1 v1, and d2 of x square minus 1, and this will be the last term of this. You will see that the second derivative of x square minus 1 will be a constant, and the third derivative will be 0. So do not write the next terms, because all those terms will go to 0, right? Now the right hand side, equal to 2n and n plus 1 c0, dn plus 1 v, and d0 of x. d0 means 0th derivative, you need not to derivate it actually, right? Plus n plus 1 c1, d this minus this, that will give you n v, and d1 v, sorry, x. Okay, fine. Second derivative of x will be 0, so I will stop here. Now I will evaluate these coefficients. You have to note that nc0 is always 1, nc0 is always 1, nc1 is always n, nc2 is nn minus 1 by 2 factorial, nc3 is nn minus 1, n minus 2 by 3 factorial, and so on, right? So I will use those direct results here. So first term, you can see that this will be 1, n plus 1 c0 will be 1, dn plus 1 v1, watch it closely. You have to differentiate v1 how many times? N plus 1 times. This is already differentiated once, since we have 1 here. So it is already derivated once, and you have to derivate it how many times? N plus 1 times. So in that case, this n plus 1 will be added here. So ultimately it will become vn plus 2, right? So vn plus 2, it indicates that v has been differentiated how many times? N plus 2 times, right? d0 means do not differentiate this thing, just write this thing, x square minus 1, right? On the next term, n plus 1 c1, that will be n plus 1, and dn of v1, this again, this power of d will be added to this suffix, that will become vn plus 1. d1 means differentiate once, this will get 2x, then this thing, n plus 1 c2, that will become n plus 1 n over 2 factorial, right? N plus 1 c2 will be this, right? And then dn minus 1 of v1, this power will be added here, that will become vn, right? Now d square of x square minus 1, that will be 2, okay, equal to, on the right hand side, 2n is already outside, and n plus 1, that is 1, that will become v n plus 1, right? Okay, d0 of x, that is x, plus n plus, that will become n plus 1, and differentiation of x with 1s, that will be 1. So ultimately we will be left with this, right? Now you can see that this is the first term, x square minus 1 vn plus 2, this is the first term. Then the second term containing vn plus 1, I will put across here vn plus 1, and here I also have vn plus 1. So there are two terms having vn plus 1. If you see them closely, then 2nx vn plus 1 will be cancelled out. So ultimately I will be left with something like 2x vn plus 1, right? And now the terms containing vn, I will put a circle in those terms. Where is that? 1 plus, here I should have something. Yeah, I missed that. dn of v, that should be vn, right? So I will put a circle here. These two terms are similar, right? And this 2 and 2 can be cancelled out, right? So n plus 1, okay, and that will come there, then that will become minus here. Minus of n into n plus 1 vn equal to 0, right? And you can multiply this equation by minus, so that will become 1 minus x square vn plus 2 minus 2x vn plus 1 plus n plus 1 vn equal to 0. So this is a differential equation having this as solution, right? What you have done, you have a function v is equal to this much, and you have differentiated it once and then apply Leibniz rule to get a differential equation of order n plus 2. This is a differential equation. This is actually vn plus 2 means dn plus 2 or dxn plus 2 of v. It means this dn plus 2 dxn plus 2 of v. It means that this is the n plus 2th order differential equation, right? So we can say that v is a solution of this differential equation, which is of that much order, n plus 2 order, right? Or you can say that, you can write it this way also, 1 minus x square, let's see, vn, right? This is n plus 2th derivative. So if I write vn and write this double dash, vn is the term and differentiated twice, that will be vn plus 2 ultimately, right? Similarly, minus 2x vn and differentiated once plus n plus 1 vn equal to 0, right? So is a differential ODE, I should write ordinary differential equation, is an ODE in Vn. Now it becomes an ordinary differential equation in the variable Vn. I have written in that fashion that it appears that it is a differential equation in Vn, right? See the second derivative of Vn, here we have first derivative of Vn, and here is the 0th derivative of Vn. So it is a differential equation in Vn, right, of second order. I should write second order, is second order ODE in Vn, right? And if you watch this differential equation closely, it is similar to Legendre's equation. I will write the Legendre's equation, which is similar to Legendre's equation, and that is, what is that equation? 1 minus x square, that was y double dash, minus 2x y dash plus n plus 1 y equal to 0. However, we have written k here, but I have replaced that k by n in this video, right? So these two equations are similar, right? And you know that this differential equation, Legendre's differential equation, has the solution p and x, right? Has solution p and x, this differential equation, and this differential equation has solution v and x, right? Or should I write v and simply? Okay, so it means that these two solutions must be multiples of each other, right? You know that the theory of differential equation, when you have two solutions of same differential equation, they are constant multiples of each other, right? Suppose you have a differential equation y double dash plus y equal to 0. The simple in order. It has solution of the form y is equal to a cos x plus b sin x. So if you say that cos x is a solution of this differential equation y double dash plus y equal to 0, it indicates that any multiple, constant multiple of cos x will also be its solution. And same thing is happening here. We have two differential equations which are very similar, right? In place of Vn we have y, right? Okay, and what is y? Y is actually Pnx, because the solution of this differential equation will be y. The solution of differential equation will be Vn, right? And y is actually Pnx that we found in our last video, right? And this differential equation has solution Vn, so we cannot say that Vn and Pnx are equal. No, they can be constant multiples of each other, right? So this is a theory of differential equation which will be used here again, right? So we can say that we can say that one of the solution Pnx should be the constant multiple of the other solution, right? So Pnx is equal to C times Vn, where C is a constant, right? Where C is constant, right? Now, yeah, that is Pnx equal to C times Vn. Vn means dn dxn of v, right? And a derivative of v, right? And what is v? V is actually this much, x square minus 1 whole to the power n. So I will replace it by its value dn dxn x square minus 1 whole to the power n, right? And again I will apply that formula c, and this can be replaced by capital D to the power n, right? So that will become dx minus 1 to the power n x plus 1 to the power n, right? Where I have used the operator capital D, which is d by dx. Now again we are at a situation where we have to find the nth derivative of some function. Again I have to rely on this Leibniz rule. We have two functions, this is u, this is v, and I have to find its nth derivative, so I have to use that Leibniz rule again, right? So treating this as u and this is v, I will write that okay, I will write that here equal to c times the first term is nc0, you see that formula, nc0 d this minus this n of u, where is my u? X minus 1 to the power n, and d this lower suffix 0 x plus 1 to the power n. This is my first term. Now we'll write the second term, nc1 d n minus 1 of x minus 1 to the power n, and d this lower suffix 1 x plus 1 to the power n, and so on, right? Okay, it will become nc0 is always 1, you know that, and dn of x minus 1 whole to the power n, you can see that this is a polynomial of degree n, and you are going to differentiate it n times, so you will get a constant, and there is n factorial. Nth derivative of x to the power n is n factorial, right? So you have x minus 1 to the power n, right? So its nth derivative will be n factorial. We are using those results directly, okay? And d0 means do not differentiate this thing, x plus 1 whole to the power n. This is the first term. Now second term, nc1 is always n, dn minus 1 of this thing. Now be careful at this point. Suppose you have x to the power n, and you are going to differentiate it n minus 1 times. So the result will be n factorial multiplied with x, right? For example, you can get x to the power 10. If you are going to differentiate x to the power 10 times, the result will be 10 factorial. But what is the answer if you differentiate it 9 times, 1 less than its power? The result will be 10 factorial multiplied with x. Or you can say that you should just integrate the next result, right? Differentiating it n times, this thing, x minus 1 to the power n, you are getting how much? N factorial, right? And what do we need here? You need n minus 1th derivative, the previous derivative, right? So the previous derivative can be obtained by just integrating the next derivative. That is, I will just integrate this thing, right? So integration of this thing will be n factorial into x, but do not write x. Our function was x minus 1, so x minus 1. So this will be the answer, right? So be careful at these points, because you cannot actually evaluate the n minus 1 derivative of this thing. That will be difficult. So just integrate this thing, this much, right? And now see this. What is the answer of this thing? First derivative of this thing, that will be n x plus 1 to the power n minus 1, and so on, right? So this is a p and x. Now what if I put x equal to 1, right? Actually, what do I need? I need to find the value of this c. Where is this c? This is my c. I need to just see the constant. What is that constant? We have to find its value. So what I am doing, I am trying to find the value of c, and I have reached almost my goal. I will put x equal to 1. Then what will happen? Pn1 equal to c. This will become n factorial, and 1 plus 1 will become 2, and this will go to 0, and the next terms will also contain x minus 1, higher powers of x minus 1, obviously, because if I write the next term, that will be of the type, see, here I will have nc2 and n minus 1 by 2, here I will have whatever it is n factorial x minus 1 whole square by 2 factorial. I will just integrate this term to get the next term, right? So ultimately, in all of the next terms, I will have x minus 1, right? So putting x equal to 1 will produce 0 in each and every term, right? Okay, now I need to find value of c, but I already know the value of pn1 that we obtained in our last video. Pn1 is equal to 1, since all of those Legrange's, Legendre's polynomials pass through 1 1, right? That is a condition that was imposed on those polynomials in order to get the bounded behavior at x equal to 1. I have explained that thing in our previous video, so I'm just using that. Using the fact that pn1 is equal to 1, I will get 1 equal to c times n factorial to the power n, and from here I will obtain the value of c, and that is this much, right? So putting the value of c here, where is that? Here. I will call it equation number 1. Therefore, equation 1 gives Pnx is equal to the value of c, 1 over n factorial 2 to the power n dn dxn x square minus 1 to the power n, which is called Rodrigues formula, right? This is the proof of Rodrigues formula, and yes, why it is important? Actually, this formula can gives the value of p0x, p1x, p2x by just plugging the value of n equal to 0, 1, 2, 3. I will put those values. If you put n equal to 0, what will get? We will get c p0x, right? And 0 factorial is 1, 2 to the power 0 is 1, and x square minus 1 to the power 0 is 1. So ultimately, you will get 1, and this is indeed correct, right? If you put n equal to 1, right, we will get p1x 1 over 1 factorial 2 to the power n 1 factorial into 2 to the power 1, and d by dx, first derivative of x square minus 1. I think you will get 2x and then x, and this is also correct. P1x is actually equal to x. If you put n equal to 2, you will get p2x is equal to, put n equal to here, 1 by 2 factorial dot 2 square, second derivative of x square minus 1 whole square, and this will become x to the power 4, then 4x cube, and plus 1, that is okay with 0, minus 2x square, so minus 4x, right, and 12x square minus 4, yeah. So ultimately that will be 1 upon 8 and 12x square minus 4, and on calculation it is giving the correct result, yes, 3 by 2 x square minus 1 by 2, which is indeed correct value, right? So you can obtain the Legendre's polynomials from this Rodrigues formula, right? So in this video, what we did, we tried to obtain those Legendre's polynomials not with the help of that Legendre's equation, right? Rather, we did some separate path to achieve those polynomials, right? So this is it for this video. In the next video, we will be doing some more applications of these polynomials. That will be part of our next video. For this video, thanks.